Topic for today will be snarks. Um, so that's probably why everyone is here, is to learn about snarks. So we're finally now at the point where we can see how snarks actually work. So we'll see how to very sort of easily, at least conceptually speaking, obtain a snark by combining the GKR protocol with a polynomial commitment scheme. And so I've said previously roughly what polynomial commitment schemes are, so I will remind you of that today, and then I will sketch how some polynomial commitment schemes work. This will only capture like a class of polynomial commitment schemes. And the point of this sketch is really just so that you just have some idea of how they work. So my plan for the next several weeks is the following. So today we're going to see snarks derived from the GKR protocol. I think next week we'll discuss Spartan, which is a snark which like the sumcheck protocol, like the GKR protocol, is also based on the sumcheck protocol, but has a different cost profile, which I'll explain a little bit about today, the comparison. And then I think the following week we'll discuss Marlin, which is a snark based on univariate polynomials, whereas anything that uses the sumcheck protocol is always based on multivariate polynomials. And my presentation of Spartan and Marlin will sort of just treat the polynomial commitments as a black box, which is what today I want to say a little bit about opening that black box, just so these polynomial commitments don't seem like completely magical cryptography that everyone just has no idea how they work. I'd like you to have some idea how they work, so that I feel less bad about treating it as some abstract black box primitive in the next couple weeks. I think after we discuss Spartan and Marlin, I will discuss front-end techniques. So this is basically techniques to take high-level computer programs and turn them into circuits, which then all of these snarks that I've listed here, whether based on the GKR protocol or Spartan or Marlin, the front end spits out a circuit that you can then apply any of these snarks to. So a circuit that you can apply. So the front end spits out a circuit that one can apply any snark to. So let's say Spartan or Marlin or a GKR protocol based snark. Examples include the SQL or Hyrax or Libra too. Okay. Yeah. So this is probably 1 week each. So this would be like next week. This would be the following week. This would be the week after that. Maybe 2 weeks for front ends. And once we cover these topics, maybe I'll say 2 weeks for front ends. You basically understand everything about snarks except for 2 things. And so one of those things is full details of how polynomial commitment schemes work. Right. So again, when I present like Spartan and Marlin and today GKR protocol based snarks, I'm essentially going to just black box the polynomial commitment schemes, other than this little discussion that's very sketchy about one class of polynomial commitment schemes. So we'll actually wind up spending a while. It could be as much as a month or something. Discussing polynomial commitment schemes, because there are several different approaches to designing them. It's a very rich design space. Basically, polynomial commitment scheme is roughly like half of any snark. So it takes a long time to cover all the polynomial commitment schemes. Yeah, so probably in weeks 5 to 9, we'll be discussing polynomial commitment schemes. And I guess somewhere in there, there'll be a week that discusses how to achieve zero knowledge. And the techniques tend to be related. So some of the ways, so I think the right way to design a zero knowledge snark is to design a snark that isn't zero knowledge, and then think about how to render your non-zero knowledge snark zero knowledge, typically by adding some extra cryptography on top of it. And the cryptography that is used to make things zero knowledge is closely related to the cryptography used to develop the polynomial commitment schemes themselves. So this is sort of my plan moving forward. We won't be totally done then, because we'll still want to talk about like recursion and folding. So things like Nova here, and we'll still want to talk about the one class of snarks that doesn't quite use polynomial commitment scheme, although it's very similar. Which is Gross 16 and its predecessors. Okay. So that's the plan, kind of long term for the rest of this reading group. So in summary, yeah, today we're going to see how to obtain snarks in a very straightforward way by combining the GKR protocol with polynomial commitments. I'm then going to give you just a little sketch about how some polynomial commitment schemes work. And then in the coming weeks, I will describe other popular snarks, just treating the polynomial commitment schemes at that point as a black box. And then eventually I will fully open the black box, beyond the little sketch today. And we'll actually spend several weeks covering various approaches to designing polynomial commitment schemes. Okay, so before I review the last week's coverage of the GKR protocol, let me just pause and see if anyone wants to ask any questions. Okay. So yeah, let's just briefly review basically the problem the GKR protocol solves and what its costs are. So the problem is circuit evaluation. In particular, it deals with what are called arithmetic circuits. So I'll remind you in a moment what that means. But yeah, so the prover and the verifier agree on a circuit C. Again, I'll remind you in a second exactly what kind of circuit. And a public input X. Public means that both the prover and the verifier know X. And let's say they also agree on claimed outputs. If the circuit has more than one output, it very well might, Y. And then the GKR protocol lets the prover actually prove that if you evaluate the circuit C on input X, the resulting outputs are Y. And the point of this is to sort of offload the hard work of evaluating the circuit on X to the prover. So it really, kind of only mainly makes sense to use the GKR protocol if evaluating the circuit is pretty expensive, because it's all about saving work for the verifier. Okay, so if the circuit has, let's say, S gates, and think of S as just as an example, say S is the size of the input N, say cubed, just as an example. So the circuit is like way bigger than the input. Then if the verifier evaluated the circuit on its own without help from the prover, it would take time, at least S in general, because in general, the fastest way to evaluate the circuit is just to go through every gate in the circuit and evaluate that gate. And if there are n cubed gates in the circuit, obviously that takes at least n cubed time. But with the GKR protocol, so this is, and I'm now going to summarize the cost of the GKR protocol. The verifier time is only the following. So it's the verifier has to read the input to the circuit. Yeah, maybe I'll read. So n is the size of the input. So the input we're thinking of as a list of like n field elements. And the verifier has to read the input. Okay, it actually does a constant factor more work than just read the input. And it has to like read the proof that the proof sent by the GKR protocol prover, and that proof length turns out to be the circuit depth times at most the logarithm of the circuit size. Okay, so this D is the circuit depth. Okay, and for many circuits, this depth will turn out to be just order log of the circuit size. Okay, in which case the verifier time is order, time to read the input plus log squared circuit size. So, assuming the circuit is not like exponentially big in the size of the input, this is a low order term for the verifier cost, which would mean order n time for the verifier, which is optimal up to a constant factor. Because just reading the input takes time n, since the input has length n. Okay, and in particular, if the circuit has size much bigger than n, like it is size n cubed, then this is a massive runtime savings for the verifier compared to ignoring the prover and evaluating the circuit on her own. Okay, so that's the verifier time. It's read the input and read the proof up to constant factors. And again, the proof has length equal to circuit depth times log circuit size. And that's an upper bound, and for some circuits, it could even be a little smaller than that. So that the proof length, this is in terms of number of field elements sent, but it's depth times log circuit size. Okay, and then finally, it's known how to implement the prover in the GKR protocol in time, linear in the circuit size. And this is of course also optimal up to a constant factor. Because just evaluating the circuit gate by gate requires time, at least one step per gate of the circuit, and circuit size refers to the number of gates in the circuit. Okay. Now just to be clear, the fact that you have to go through evaluating a circuit can itself lead to massive overheads and costs for the prover, especially. We'll discuss this more when we discuss front ends in a few weeks, but the very nature of having to if the prover really is claiming that it knows some witness and satisfying some property, the witness is supposed to be a secret key that controls corresponds to some public key on the Bitcoin network or something, and so the circuit is really implementing an algorithm that kind of takes as input the secret key and the public key and checks that the secret key sort of matches the public key. Having to express that computation in a circuit format in order to then apply the GKR protocol could itself be super nasty. Like a lot of computations sort of are very unnatural to express in a circuit format. I have this blog post that I wrote not so long ago that talks about, kind of breaks down the costs of any snark into what I call front end costs and back end costs. And the front end costs sort of cover kind of the nastiness that comes from having to represent the computation the prover is claiming to have run as a circuit. So this is sort of badness of needing, to use a circuit. So certain operations that take one time step on your laptop might take sort of many gates of a circuit. And then the back end overhead or cost is like the extra cost, to prove for the prover to prove it evaluated the circuit correctly compared to just evaluating the circuit with no proof of correctness. And kind of the end-to-end costs of your snark turn out to be the product of the front end costs and the back end costs, right? So if your circuit is 100 times bigger than the number of steps your computer program runs for, because like each step of your computer program turned into 100 gates of the circuit or something, right? And then the prover takes, say, 1,000 times longer to prove it evaluated the circuit correctly compared to just what it would take to evaluate the circuit with no proof. Then your total overheads, if you didn't have to go through a circuit and didn't have to prove you evaluated the circuit correctly, would be, the product of, how much bigger is the circuit than the runtime of the computation you started with, times, how much more expensive is it to prove you evaluated the circuit correctly than if you didn't have to prove it. And so in this case, while the first cost is sort of 2 orders of magnitude, and the second cost is 3 orders of magnitude, and maybe individually those don't seem so bad, their product is 5 orders of magnitude, which is not something you can ignore. So what this is saying here about the prover running in time, linear in the circuit size in the GKR protocol, is that the backend overhead of the GKR protocol is just a constant factor. Now, in a snark, there'd be other things happening. A snark derived from the GKR protocol, there are other things happening other than the prover running the GKR protocol. So, this whole GKR prover time being a linear in the circuit size is only referring to some of the stuff that the final snark prover winds up doing. But anyway, the conceptual message here is that the prover is only a constant factor, slower than evaluating the circuit gate by gate. But again, that's just referring to back-end costs. The front-end costs can still be really substantial, just by virtue of the GKR protocol being phrased in terms of a circuit evaluation problem. Okay, so those are the costs of the GKR protocol. Please interrupt with any questions, but if no one interrupts, I will just briefly remind you in a little more detail what kind of circuit am I referring to? Okay, so just to draw a little example, let's say the public input X has length 4, so it consists of 4 field elements. Let's say those field elements are 3, 0, 2, 4. So the most basic kind of arithmetic circuit consists of gates and wires, where the gates compute addition and multiplication operations. So right, the input here is field elements. So 3, 0, 2, and 4 are entries of some finite field. Any field comes equipped with addition and multiplication operations. And so those are the addition and multiplication operations that I refer to here with these gates in the circuit. So here, we have like these first 2 gates, like this first gate. Okay, so I'll just get back to it then. So in this little circuit example I'm drawing, so the gates are addition and multiplication operations. So here, this third gate I'm drawing is an addition gate that computes the sum of like the second and third inputs. So that's the circuit. So let's say these are the 2 output gates here. So these would, what I just boxed in red would be the 2 output gates. And if you're just naturally going to evaluate the circuit gate by gate, it would look at like the following. Like so this gate that squares the first input would have value 9 because that's 3 squared. This one has value 0. This has value 2, 16. This would be 0. This output gate would have value 0 because 9 times 0 is 0, and this one would have value 32. So like, in practice today, people like to use kind of generalizations of these very simple arithmetic circuits I'm describing today. That's actually one sort of downside of snarks based on the GKR protocol. You can sort of extend the GKR protocol to support more general gates than just addition and multiplication. and so forth. But it is a little less flexible in terms of the kinds of circuits it can handle, compared to the things people typically like to use today. And a final assumption kind of made by the GKR protocol is that the circuit is layered, and also that it has fan-in-2. Fan-in-2 means that every gate computes the sum or product of two other gates. And layered means that you can kind of partition the gates into layers, so that any gate at like layer I it only has is only fed values from gates at layer I plus 1. Okay, so that's the GKR protocol, and that's arithmetic circuits. And yeah, so again, circuit evaluation is just the problem of the prover kind of establishing what is the output of this agreed upon circuit C when evaluated on agreed upon input X. Yeah, that's what the GKR protocol is all about. Okay, that's the recap. Anyone want to ask any questions before we start talking about snarks derived from the GKR protocol?
Yeah, I just have a quick question regarding the name. So you talk about arithmetic circuits, and sometimes heard about algebraic circuits, and I just wanted to know if there's some difference or a nuance or nothing at all.
Yeah, so when you say algebraic circuits, by any chance are you referring to algebraic intermediate representation, or do you mean algebraic circuits, which might be potentially something else?
No, specifically algebraic circuits.
Okay. I think anyone who refers to algebraic circuits actually would be discussing arithmetic circuits, I think.
Okay.
I think there's a topic called, I guess, like algebraic. I guess people call it algebraic complexity theory, which is if you've ever seen notions of like VP, which is some kind of algebraic analog of the complexity class NP, this is exactly what they're discussing. And they're basically discussing the power of arithmetic circuits. I think that you wind up with subtleties whereby, like sometimes people only care about the input-output behavior of the circuit, so they kind of call two circuits equal, so long as on every single input they produce the same output. Whereas other times they only call the two circuits equal if they actually compute the same polynomial. And those are slightly different notions. If you allow very high degree polynomials, you can have two polynomials that have the same input output behavior, but are not literally the same polynomial. So yeah, I would just say as a short answer to you, unless they're talking about algebraic intermediate representation, if they say algebraic circuits, they probably just mean what I'm saying here, arithmetic circuits.
Okay, thank you.
Yeah, thanks for the question. Other questions? Okay, and this AIR thing, this algebraic intermediate representation, that's just referring to a particular generalization of arithmetic circuits, essentially, that is somewhat popular to use in snarks in practice today. Okay, so let's discuss snarks from the GKR protocol. Let me discuss by just describing snarks. So I probably did do this on maybe the first meeting of this reading group. But I think it's useful to do it again. It doesn't take that long. So in a snark, the prover claims to know some witness, let me call it W, satisfying some property. Yeah, I like the example of, somebody claims to know like the private key that controls a certain Bitcoin address or something. And the trivial proof that the prover knows this witness is to just actually send the witness to the verifier, and the verifier can just directly check that the witness satisfies the claim property. Okay, yeah, another example might be, you might want to use a snark, like a roll-up might say, hey, like I have a bunch of blockchain transactions And I don't want to have to post all the digital signatures on chain, because then every blockchain node in the world has to store those signatures and check their validity. So instead, I'm just going to, so the trivial proof that I know all these signatures would be to just send the witness, it would be the signatures, to the verifier, in this example, the blockchain, which would have to directly check that all the signatures are valid. Okay. And the idea of a snark, and the reason a snark would be useful in exactly this blockchain application I just described, is it will achieve the same effect of convincing the verifier that the rollup actually knows all of these signatures that authorized all of these transactions, but with better cost for the verifier. Okay, and in particular, we're interested in making sure that the proof is shorter than the witness, than the trivial proof. And ideally, we'd also like the verifier time to check the proof to be faster than the time taken required to check the witness for validity. Okay, and in like a rollup, both of these things matter because it costs gas to store information on the blockchain, so storage is expensive, and it also costs gas to force all the blockchain nodes to do computation, like checking digital signatures. So basically, memory and time are both real world compute costs. And if the verifier is, the blockchain, we want to minimize both of those costs for scalability reasons. Okay. Now, let's say for a moment that we're going to forget about making the proof shorter than sending the whole witness. So let's just forget about this for a second. Let's focus on saving the verifier time only for a second. So in this case, it's very, very easy to use the GKR protocol. So here's the situation. We could have the prover send the witness to the verifier. And just as in the trivial proof system, but rather than having the verifier directly check the witness for correctness, we could let let C be an arithmetic circuit, be a circuit that takes W as input and applies like the witness checking procedure to W. Right. So in the rollup example of trying to keep digital signatures off chain, that witness checking procedure would just kind of take as input the witness. I guess it would also, either the witness itself includes other transaction data, like the accounts that the transactions were initiated from or whatever. Or those that extra data, like the list of accounts might be part of the public input. So this circuit might take as input, now it might have, kind of two pieces. So either like it might just be this witness W, or there might also be a part of it that I will call X. So here, yeah. Anyway, I'll get into this more in a moment. But anyway, so yeah. So basically, what the circuit does is it just implements the procedure that the verifier would apply to W if it were willing to do the hard work of checking W for validity. So for the digital signature example, basically the circuit would just be checking the validity of all the digital signatures in W. So in that example, it would be the circuit would be check validity of all digital signatures in W. Thereby confirming that indeed all of the transactions the rollup is trying to process have been authorized by the initiators of the transactions. Okay. And then, the point of representing the witness checking procedure as a circuit is that then, rather than the verifier directly compute, like applying the witness checking procedure itself to the witness, which we're thinking of as taking a lot of time, we can use the GKR protocol to force the prover to apply the witness checking procedure to the witness. So that is to evaluate C of W and convince the verifier that the output is, whatever output denotes like the witness passed the checks. Let's say that output would be 1. 1. Question? No? Okay. Okay, great. So that is sort of a direct way to use the GKR protocol to save the verifier time compared to the trivial proof system of the prover sending the witness and the verifier checking the witness for validity itself. But in a snark, we don't just want to save the verifier time. We also want the proof to be shorter than in the trivial witness. Okay, and that is where polynomial commitment schemes comes in. But before I remind you what is a polynomial commitment scheme, let me remind you of a key property of the GKR protocol. Okay, so recall that in the GKR protocol, and this is not unique to the GKR protocol, like basically any interactive proof winds up having this property. The only information the verifier needs to know about the input to the circuit, so I'm calling that input right now W, is a single evaluation of the multilinear extension of W. Okay, so that evaluation happens to be at a randomly chosen point R. Okay, so yeah, the GKR protocol has this property which seems maybe amazing if you've never seen it before, but sort of just falls naturally out of the interactive proof machinery we have, which is that if the prover claims that C of W equals Y, okay, the verifier can run the whole protocol without even knowing W for almost the entire protocol. So the verifier doesn't need to know W to run the whole protocol until the very, very end. And even then, at the very, very end, it doesn't need to know all of W. It only needs to know a single evaluation of the multilinear extension of W. So W twiddle, as a reminder, is the multilinear extension of W. This is the unique multilinear polynomial that is degree at most 1 in each variable, so that kind of when you evaluate it at any Boolean input, it spits out the associated entry of vector W in a sentence. We've talked repeatedly about multilinear extensions. So they're discussed in chapter 3 of the book, and we've discussed them in this reading group repeatedly over previous sessions. Okay, so this is kind of amazing. It says this evaluation of W twiddle of R, this is one field element. Okay, so intuitively, it feels a little bit wasteful that we had the prover send the entire witness to the verifier. Like, why did the prover have to send all of W if the verifier only ultimately needed to know a single field element, W twiddle of R? Okay, and that's exactly how you get a snark from the GKR protocol, is by kind of leveraging this observation to avoid the prover having to send the entire witness to the verifier. Okay, but the thing you have to be really careful about here is the following. So here is, I guess, sort of the key attack that we're going to need to prevent if we don't want the prover to just send the whole witness to the verifier in full. Okay, so the key thing we have to be aware of is that if the prover knew what point R, so it knew the evaluation point R that the verifier was ultimately going to evaluate W twiddle at, so that the GKR verifier was going to evaluate W twiddle at when it chose W, right? Then it could sort of trivially choose a W, so choose an invalid witness. So it's like not a witness, an invalid W, such that W twiddle of R, equals say W prime twiddle of R for a valid witness W prime. Okay, what's happening is the security of the GKR protocol, as with any interactive proof, like really depends on the unpredictability of the verifier's random challenges. So the prover has to kind of send messages throughout the interactive proof before it learns what the next verifier challenge will be. And in particular, if the prover knew at the start of the protocol what the final kind of random verifier, vector R would be, it could trivially cheat. It could trivially convince the verifier to accept a false claim as valid. And the way it would do that is just simply take an invalid W that agrees with a valid witness W prime just at the one point that the verifier is going to inspect, namely R. So basically, since the verifier only looks at W twiddle at the single point R and otherwise doesn't know anything at all, doesn't need to know anything at all about the witness, it just cannot tell apart two inputs that agree, whose multilinear extensions agree at R. And that's not an issue for security, it turns out, if the prover does not know R, like when it's choosing like the input to the circuit. But it's a huge problem. It completely breaks security if the prover can choose the input to the circuit to depend on this point R. Okay, so in our snarks, this is what we're going to have the prover do. So here's the snark. So I'm going to sort of describe the functionality we need from a polynomial commitment scheme in the process of defining the snark or describing the snark. So, okay. In the trivial proof system, the prover would send the witness W in full to the verifier. Instead, we're going to have the prover cryptographically commit to W rather than sending it in full to the verifier. And more precisely, it'll commit not just to W, but to the multilinear extension polynomial W twiddle. Okay, so that's one message from prover to verifier. And this commitment, this cryptographic commitment, is typically just a single hash value, typically, or a single element of a cryptographic group. All right, and so like a single hash value is typically just like 256 bits. A group element might be 381 bits or something like that. So even if the witness is really big, this cryptographic commitment to the witness will be really tiny, just like 256 bits or something. Okay, and the idea is this is sort of mimicking the prover sending W in full to the verifier, but the prover isn't sending W in full to the verifier. It's sending only like a single hash value or something like that. Okay, so in your head, just imagine the prover has explicitly sent W to the verifier, even though it hasn't. It's only cryptographically committed to it. And I'll explain in more detail in a moment what commit even means here. Okay, then they run the GKR protocol. To prove that applying the circuit to the witness results in output 1. Okay, at the very end of the protocol, the verifier needs to know W twiddle of R. Okay, unfortunately, it doesn't know W twiddle of R because the prover has not actually sent W to the verifier. It only sent a single hash value, the cryptographic commitment to W twiddle. Okay, so what we need from the commitment scheme is a way for it has to allow the prover to, so P sends W twiddle of R to the verifier. And of course, the prover is entrusted to do this honestly, right? So the commitment scheme needs to come with the following functionality. It needs to let the prover provide what's called an evaluation proof. That is a cryptographic proof that the value sent is indeed the committed polynomial evaluated at R. Okay. So the way you think of the commitments, okay, is while the commitment is just a single hash value or something, so it's really small. You think of it as like a box that contains the entire polynomial W twiddle inside of it. Okay, so it's like we took this giant vector W, or more precisely, its multilinear extension polynomial W twiddle, and we like shoved it inside this tiny box, and we sent just the tiny box to the verifier. Now, if the verifier were to actually insist that the prover open up the box and take all of W twiddle out of it, well, that's going to destroy the verifier time and the size of the proof or whatever, just because W twiddle is so big. So fortunately, the verifier only needs to know not all of W twiddle, but just a single evaluation of it. So what we insist is that the commitment scheme used provides a way for the prover to just provide just that evaluation and prove to the verifier that the returned evaluation is actually the polynomial that lives inside the box evaluated at the one point the verifier cares about. Okay. And then what does, formally, what does cryptographic commitment mean? So commitment means the key property is something called binding. And that says once the prover, sends the commitment, okay, it cannot change its mind about what polynomial lives inside that box. So it's like it locks, sending the commitment is like locking the box, so that the prover itself can't actually open the box anymore and change what's inside of it. So the prover cannot change the polynomial inside the box. So the polynomial that's committed. Okay, and this is exactly meant to prevent the attack I mentioned before, whereby, so the worry is, once the verifier sends the prover, R and says, hey, prover, you need to tell me W twiddle of R, where W twiddle is whatever polynomial lives inside the box. Okay, if at that point the prover could alter the polynomial inside the box, now that it knows R, okay, then soundness would be completely out the window. Okay, but a cryptographic commitment scheme is binding. Okay, which means that once the prover sent that commitment, it can't change the polynomial inside the box. So it's completely as if the prover had just sent the whole witness to the verifier, like at the start, as far as the prover's inability to change its mind about what is the witness goes. Okay, so that's what I mean that by saying that the cryptographic commitment scheme is kind of used to simulate the notion that the prover sent the whole witness to the verifier without actually forcing it to do that. The binding property of the scheme achieves the same effect, the key effect being that once the prover sends the commitment, it can't, kind of change its mind about what witness it has sent to the verifier. Okay, so that is snarks from the GKR protocol. That's it. The only details I'm hiding from you at this point is how this cryptography works that allows the prover to cryptographically commit to W twiddle and then later reveal a requested evaluation of W twiddle, as well as a proof that the revealed evaluation is indeed the committed polynomial evaluated at the requested point. So the cryptographic protocols that achieve exactly that functionality are called polynomial commitment schemes. Okay, and essentially, the rest of today's session will just be giving a sketch of how some of these commitment schemes might work. Okay. But before we dive into that, let's pause, and I'll see if there are any questions. And I'll briefly describe, before discussing the sketch of polynomial commitment schemes, I'll briefly describe some of the snarks based on the GKR protocol and how they compare to other snarks that people are using today. So yeah, first let me see. Does anyone want to ask anything? Okay, can someone confirm I haven't like dropped off the call again or anything like that, since I've been having so many problems with Discord?
You're good.
We can hear you. Yeah.
Okay, great, thanks. Okay, great. Yeah, so just summarize one more time. The prover, uses a polynomial commitment scheme to commit to the multilinear extension of the witness. They apply the GKR protocol to prove that the circuit evaluated at the witness, produces the claimed output. Right. The verifier in that protocol for the entire protocol does not need to know anything about the witness until the very, very end, when it needs to evaluate the multilinear extension of the witness at a random point. And the polynomial commitment scheme has to provide the functionality that it lets the prover provide that evaluation, as well as a proof that the provided evaluation is indeed the committed polynomial evaluated at the requested point. So that's the snark.
I have kind of, I guess, a question about so if this is a snark, does that mean what you're trying to say is this is the general structure of all snarks, and you can replace GKR with something else, and all polynomial commitment schemes kind of have the same thing where you commit and then do an evaluation proof at the end?
Yeah, that's exactly right. And I'll say a little bit more about how other snarks kind of differ from roughly speaking, some most of the snarks people use today, they will kind of swap out the GKR protocol the GKR protocol is used to confirm that the prover evaluated the circuit on the witness correctly, and they will other snarks will swap out the machinery used to check that the prover evaluated the circuit correctly. And I'll say more in a moment about what the trade-offs are there, and why the other snarks are able to swap out, not use the GKR protocol. And the short version is that they sort of use more cryptography. So that comes with trade-offs, right? Because cryptography is expensive for the prover. The more cryptography you use, the more time the prover is spending on cryptographic operations. Yeah, so basically, at a high level, all snarks are obtained by combining something called a polynomial IOP with a polynomial commitment scheme. Okay, and there are some caveats to this, which I'll discuss in more detail at some later point. But I also, every time I give a talk on snarks, I describe exactly this and as the introduction and give the caveats. Okay, and so if you give me any polynomial IOP, and I'm not telling you, today what is polynomial IOP, don't worry about it. And you give me any polynomial commitment scheme, you can, with some caveats, you can put them together to get a snark. Okay, so different snarks obviously use different polynomial commitment schemes, and in the GKR protocol based snarks, basically the polynomial IOP more or less is the GKR protocol. But there are other polynomial IOPs you could give, so Spartan has another one that's also based on the sum check protocol, but unlike the GKR protocol, which applies sum check once per layer of the circuit, Spartan kind of applies the sum check protocol only once, maybe twice, but let's just say only once for the whole circuit, once for the whole circuit, rather than once per layer. And then Marlin and Planck give still different polynomial IOPs, which, as I mentioned earlier today, are based on univariate polynomials. The book calls these polynomial IOPs, just calls them constant round polynomial IOPs. The distinction being that if you use the sum check protocol from chapter 4, you're always going to have logarithmically many rounds in the size of the circuit you deal with. Whereas if you use univariate polynomials as sort of the technical machinery underlying your snark, You can cut logarithmic rounds down to constantly many rounds. Yeah, so that's the summary of the design space. This is actually a pretty complete summary. And so, yeah, when I say like you can get a snark by like kind of taking the GKR protocol for circuit evaluation and just combining it with any polynomial commitment scheme to commit to the witness, it's all very modular. That you can kind of swap out the GKR protocol for some other technique to deal with the prover like establishing it evaluated the circuit correctly. And the polynomial commitment scheme is used to like avoid having the prover like send the whole witness to the verifier. And the one sort of conceptual caveat, I guess I'll mention now, and this is exactly what I meant by all the other approaches sort of use more cryptography than the GKR protocol approach, is the following. Okay, so in every other snark other than GKR protocol derived snarks, the prover doesn't just use the polynomial commitment scheme to commit to the witness. Okay, the prover actually, in every snark but the GKR protocol based one, the prover uses the polynomial commitment schemes to cryptographically commit. Not only to like the witness W, but rather to the value of every single gate in the circuit. Okay. So there are some circuits. You could imagine there are some circuits where like they take as input like a relatively small vector W, and then you have this very, very big circuit, much bigger than W itself, and yeah, they spit out some output. Okay, and so with the GKR based snarks, the prover is only going to apply the polynomial commitment scheme just to W. And that's nice for prover time. Okay, because the bigger the vector the prover commits to, the more expensive, the more cryptographic operations the prover has to do. And that is typically the bottleneck for the prover. And I would say if it's not the bottleneck for the prover, it means that the other thing that is the bottleneck is more expensive than it should be. So yeah, I think it's a good heuristic in your head as a protocol designer to try to minimize the number of cryptographic operations the prover has to do. And by the way, by that I mean cryptographic operations. These polynomial commitments, the operations they tend to do that are the bottleneck are either multi-scalar multiplications, also known as multi-exponentiations. They're Merkle hashing, and we'll discuss more about Merkle hashing later today, or they're FFTs. And basically, the bigger the polynomial you commit to, the more of these operations the prover has to do, the more expensive it is for the prover. Okay, so all the other snarks would apply the polynomial commitment scheme not just to the input W to the circuit, but rather to the vector of all gate values for the whole circuit. So like if this is your input W, and then your circuit has all these other gates, right, then with the GKR protocol, the prover would just be committing only to these 4 elements. But with any other snark, the prover would be cryptographically committing to not just to these 4 elements, but also, this gate value and this gate value and this gate value and this gate value and this, every gate in the circuit.
So the idea is that you don't have to send the entire circuit either. Right.
And okay, so now you get into that question kind of gets into issues about like how this is sort of a separate issue. How does V like learn or know the circuit C? Okay, that the prover is claiming to have evaluated on W. Okay, that is actually a separate issue that we should also discuss because it's an important one. Is that the issue you are asking about right now?
Yeah, well, I'm sort of saying maybe more from a performance side, which is, that you would do some kind of, cryptographic commitment to the gates so that then V could basically just check that the full circuit is evaluated correctly at the end, but then implied in that is like it doesn't really know anything. It's just checking something random, kind of.
Yeah, I think that's the right intuition for how all of these other snarks, like Spartan, Marlin, Planck, um, work. Um, I think your intuition is exactly right. So the prover just cryptographically commits to the value of every gate in the circuit, um, and then does some magic probabilistic checking stuff to kind of check that all those committed values like respect the gate by gate operations of the circuit without the verifier ever having to kind of do any of those operations herself. Whereas the GKR protocol does not have the prover cryptographically commit to the values of any gates in the circuit other than those, I call, most people would not call these witness elements gates, but I do. So yeah, the GKR protocol derived things would only have the prover commit. So only thing committed in the GKR stuff. Okay. There is a separate issue uh, which is if we want the verifier to be to save time compared to evaluating the circuit on its own. We have this problem that if for like an arbitrary unstructured circuit, in order for the verifier even to like process a description of the circuit, the shortest description might be listing every gate in the circuit. In which case, there's literally no way around the fact that the verifier requires time linear in the size of the circuit just to even know what is the circuit that the prover is claiming to have evaluated. And there are two things to say about that. So one is a lot of circuits are what's called uniform. That's sort of a technical jargon for the idea that they contain repeated structure. So they do the same simple thing over and over again. Okay, and this is so you can always guarantee that this is the case if these circuits capture like computer programs, that were expressed for like a virtual machine or CPU abstraction, right? Because the whole idea of a CPU or virtual machine is that the computer program is just going to apply like one of a handful of primitive instructions at each step. So that is, there's some kind of very simple transition function, capturing, so the EVM, has like 140 or something primitive instructions, and the RISC-V instruction set has like 100 primitive instructions. And so programs for these virtual machines just do the same simple thing over and over again, where it sort of figures out at each step what instruction should be executed at this step, and then it executes the instruction. And so you always can turn like a computer program for such a virtual machine abstraction into a circuit with repeated structure, that just applies, the CPU, over and over and over again, one per step of the computation. In that case, the circuit has a much simpler description than literally listing like every gate in the circuit. So in that case, you can have the verifier sort of process all of the information that the underlying snark needs to know about the circuit without ever, spending time linear in the size of the circuit just to read a description of the circuit. Then even if your circuits are not uniform, and again, I think like everything people deal with in practice have some amount of uniformity to them, but sometimes there are some overheads that come in if you really want to ensure that the verifier can like pull out the information it needs about the circuit's structure very quickly. So even in like non-uniform cases, what you could do is have like an honest party sort of cryptographically commit to the circuit in a pre-processing phase. Okay, and this is actually exactly what happens in Marlin and Planck, and even like Gross 16. Although there the like the circuit commitment happens during the trusted setup, whereas in Marlin and Planck the circuit commitment the trusted setup is universal. It doesn't depend on the circuit, and the circuit commitment can happen after the trusted setup. And if you don't know what I'm talking about, don't worry about it. We'll get to these snarks soon. Yeah. So in summary, like no matter whether your circuit is uniform or not, there are ways to ensure that the verifier doesn't actually have to take time linear in the size of the circuit. Either you ensure that the circuit can kind of be described in a much more succinct way than writing down every gate in the circuit. And in that way, the verifier can kind of pull out whatever information it needs about the circuit without spending time like materializing the entire circuit. Or even if that's not the case, you can have an honest party commit to the circuit in pre-processing. So in like roll-up applications, whoever writes the smart contract that is like acting as the snark verifier would either have a commitment to the circuit sort of baked into, like hard-coded into the smart contract, or I guess you could have the smart contract take that commitment as like as input, but then you really better trust that whoever provides that input to the smart contract is doing it honestly. To be clear, the reason I'm calling this pre-processing and not a trusted setup is this pre-processing phase is what's called transparent, meaning anybody else willing to do the work can check, can redo the commitment, so can check it. So it's like it's expensive to check, but anyone can check it if they are willing to pay the expense. Right. So you want the party to be honest, but it's not what's called a trusted setup. With a trusted setup, it's not the case that anybody at any point in time can check that the procedure was done correctly. Okay, so this has turned into like a rambling, description of snarks and various issues you have to think about if you want to sort of discuss their performance and how they compare. So not a very focused discussion, but I hope it's been followable anyway. I do want to give just a very short summary of like the pros and cons of GKR-based snarks relative to these other snarks like Spartan, Marlin, Planck, and Gross 16. Let me just pause before I give that quick summary. Does anyone want to interrupt and ask anything? Okay. Okay, so I would say here are, in short, here are the pros and cons of GKR-based snarks. So I would say they typically, I think it's fair to say they have the fastest prover. Now the caveat, this might get a little fishy because the circuit model that the GKR protocol deals with is a little more restricted than these generalizations of circuits that people like to use today, like Planckish or Air or whatever. So this certainly for a given circuit size, the prover is definitely like the fastest in the GKR protocol, but the circuits might be bigger because the circuit model is a little bit restricted. Again, it's like theoretically known that you can extend the GKR protocol to not require layered circuits and to not just have addition multiplication operations. But nonetheless, it is more restrictive than things like less Planckish and R1CS and stuff like that. But yeah, so the reason for the fastest prover is basically that the prover in the GKR-based snarks only cryptographically commits to the witness, not the whole circuit. Okay, so that's the big benefit. Okay, the downside is that the proofs are pretty big. Okay, now I do want to clarify, I think the GKR protocol, the GKR-based NARCs have a reputation for having like really big proofs. I think that might be slightly overblown. So, right, the proof size is, like depth, circuit depth times log circuit size, many field elements, plus the size of like one polynomial commitment, and one evaluation proof from whatever polynomial commitment scheme you use. Okay, and like any other snark is going to have this commitment cost. Okay, so in terms of having bigger proofs than other snarks, the issue is the GKR protocol, this depth times log circuit size. Okay, so asymptotically speaking, it's actually without loss of generality to consider circuits whose depth is order log circuit size, and I can say more about this when we talk about front ends. So basically, in a sentence, it's actually known how to take any computer program that runs in time t and sort of turn it into a circuit satisfiability instance where the circuit has size close to t and depth only log t. And so asymptotically speaking, this depth times log circuit size term is just log squared circuit size. Okay. And for comparison, note that Fry is a very popular polynomial commitment scheme today, and the proof size of Fry is so there's actually an extra factor that depends on the security parameter, but let's ignore that. Log squared of the circuit size as well, hash evaluations. Okay, so people actually are quite frequently using like log squared size proofs even today. Okay, I will say I do think that the hidden constant here with the GKR protocol, I suspect is probably worse than Fry's. Although I might be wrong about that. So that's sort of the summary is like asymptotically speaking. I think while the GKR protocol based snarks have a reputation for having like really big proofs, they concretely might be bigger than stuff people are using today, but asymptotically they're actually the same. Okay, so broadly speaking, these are the pros and cons. Like if you want the fastest possible prover, you want to use the GKR protocol based snarks, basically because it minimizes the prover's cryptographic work. The cons are the proofs are bigger. And this fastest prover thing comes with the caveat that the circuit model that the GKR protocol works in is like more restrictive than the circuit model other snarks use. So while the cryptographic operations for the prover is sort of minimized using the GKR protocol relative to the size of the circuit itself might be noticeably bigger. And then here's the final, and I think maybe the most important caveat, okay, is that I mentioned, as I talked about it being without loss of generality, that the circuits have log depth, is that there are known, transformations, I call them front ends. These are transformations from computer programs into circuits. Okay. Now, these transformations, they use a lot of advice inputs. Okay, let me explain what that means. Okay, so let's say that you need to do your witness checking procedure needs to do division. Okay, so like there's some field element X, well maybe I'll call it Z, arising in the computation, like the checking of the witness, and you really need to know Z inverse. So that you need to know Z inverse. Z inverse. So that that's like the finite field version of like 1 over Z, dividing by Z. Okay. Now remember, arithmetic circuits, their primitive operations are addition and multiplication. Okay. Now doing division only using addition and multiplication is like really, really nasty. Like it's not something you want to do. So you don't want your circuit to actually like compute Z inverse from scratch. Okay, instead, what you will do is you'll have the circuit take as advice input a claimed value for Z inverse. Let me call that value, I don't know, L. And what the circuit will do is it will just check that L is valid. Okay, so it will just multiply Z by L. So here L is an advice input. L is an advice input. It will multiply Z by L, call that multiplication gate an output gate, and insist that that output value better be 1. Okay, so that's an advice input. So it's sort of a way to avoid doing nasty operations with addition and multiplication gates by having the prover kind of provide either the output of the operation or, I don't know, intermediate values that, you know, would be helpful to computing the operation. But then the circuit needs to check that those values were honestly provided. That's why they're called advice. And so the picture for the circuits that actually come out of these front ends really should be the following. So, right, like if the prover is claiming to know a witness W satisfying some property, say W is like a bunch of digital signatures authorizing a bunch of blockchain transactions, the input to the circuit is really, it's not just W. It's W and all the advice inputs. Okay, and then the circuit will sort of check that W, you know, satisfies the claim property using the advice inputs as advice to kind of help with the checking. And when you apply a GKR-based snark to this circuit, right, the prover would need to cryptographically commit not just to W, but to the advice inputs as well. So the prover commits to what's called like the witness to the circuit, which is the witness to the circuit. And the witness to the circuit is W as well as the advice inputs. Yeah, so basically, like known front-end techniques in general, the number of advice inputs is so large that it's actually a constant fraction of the entire circuit. And in that situation, I'd say like the prover time savings from using the GKR protocol is not that big. Because while the prover only commits to the inputs to the circuit and like not the whole circuit, the inputs to the circuit, because they involve the advice inputs too, they it's not that big a savings. Okay, so anyway, so that's like a very detailed summary of the pros and cons of GKR-based snarks. And I wanted to go through that both to kind of explain what I think is the right mental model for how to think about prover time in snarks, and also so that you have context as we talk about alternative snarks like Spartan, Marlin, you know, Plonk, although we won't talk about Plonk in detail, Growth 16 in the coming weeks. Because otherwise you'd be like, well, we already saw a snark. Like, why are we seeing, you know, 3 other snarks? Like, you know, we're done. The answer is there are all of these kind of trade-offs between different snarks in terms of their performance profiles. Okay, so that is what I had to say about snarks from the GKR protocol. Let me just pause one more time, and if there aren't any questions, I'll just spend maybe 15 minutes sketching how some polynomial commitment schemes work. And I'll mention this sketch I covered in my first, I think it was lecture 4 of the zklearning.org MOOC. So if you happen to be following along with that, you can feel free to just drop off since I've already taken up over an hour of your time today. But if you haven't seen that lecture, I do think the sketch will be useful. So yeah, let me just pause and see if anyone wants to ask anything at this point.
Is there a list of GKR-based snarks like hierarchs?
Yeah, I'll give you basically a complete list now. So, so the first one was vSQL, which was kind of the I think that in my view, like the main work that sort of observed that you can take anything like the GKR protocol and the polynomial commitment scheme and put them together, and boom, you get a snark. Like that's basically, I think that's the main contribution of vSQL, and that was basically the subject of today's presentation. The next follow-up was Hyrax. There was a variant of vSQL they called ZK vSQL, which just sort of made it zero knowledge. Then Libra and Virgo. Yeah, so if you want a summary of like why there are differences, so both of these were looking to achieve ZK, whereas vSQL wasn't ZK. Hyrax also gave like a different polynomial commitment scheme than vSQL used. Okay, so vSQL used variant to KZG commitments. If you don't know what they are, don't worry about it, but they require trusted setup. Hyrax gave a transparent polynomial commitment scheme, which I actually think is going to gain more relevance soon. Basically, it's got really nice properties, but bigger verifier costs. And I think you can just bring the verifier costs down with composition now. Libra, did Libra do? Libra was the paper that finally for totally general circuits got order circuit size prover time. So prior works had achieved this for circuits with repeated structure, but not for totally general circuits. They had an extra like log factor or something for totally general circuits. So Libra got order circuit size prover time in the GKR protocol. And then Virgo gave away to use Fry, which is a polynomial commitment scheme targeted at univariate polynomials. But remember, with the GKR protocol, you need the prover to commit to a multilinear polynomial rather than a univariate one. So Virgo explains how to do that. Yeah. So even though W twiddle is multilinear. So I think this is a complete list, if I'm not forgetting anything, as well as a very brief description of kind of what the contribution of each work was.
Yeah, it makes sense. I will get back to you like if I have questions after reading.
Okay, sounds great. Yeah, and there's been more recent work that's like looking at composition, like snark composition or recursion with GKR based snarks. So there was work by some folks out of Consensus. So there's some other work that I'm not mentioning here. I don't think there's like names of systems to point to in this case. I don't think. Yeah. Okay. Other questions? All right, so let's sketch how some of the polynomial commitments work. So the ones I'm going to sketch now are based on Merkle hashing. And if you want them to be non-interactive, they also use fiat Shamir, which, as we discussed several weeks ago, also only uses cryptographic hashing. So like the only cryptographic primitive that these polynomial commitment schemes use is cryptographic hash functions. Although once you're using fiat Shamir and the way these things are analyzed, they're using the hash functions in sort of a very strong way. The security proofs are all sort of in the random oracle model and stuff. Anyway, and so examples of these polynomial commitments are like Fry, Laharo, Breakdown, Orion, etc. Cool. Actually, let me poll people real fast. Just because I've taken more time than I expected, I want to know whether I should review Merkle hashing. I'm worried though that people won't want to, will want the review, but won't want to say they want the review. Let me just review it really quickly. I try because probably many of you know Merkle hashing already. I'll really try not to spend too much time on this. And if anyone wants me to spend more time on it, please just say so, and please feel comfortable about it. Because if there's one of you who wants more time on it, then there's definitely more than one of you. Okay, so Merkle hashing is a vector commitment scheme, And this is a way to, like an untrusted prover can commit to some vector of field elements. Let me call it U. And in general, it can be a vector of like any hashable data. But for polynomial commitment schemes, we're only going to, the data we'll be dealing with will always be field elements. So let's just restrict our attention to vectors of field elements. But in general, you can use Merkle hashing to commit to vectors of anything you can hash. Okay. Later, the verifier, will request the ith entry of the committed vector, for some I in 1 up to n, because there are n entries. And the prover will be able to, reveal, will like kind of open up like just that entry and provide the analog of what I was calling an evaluation proof in polynomial commitment schemes, like basically authentication information to confirm that the returned value of UI is actually the ith value of the committed vector. So again, this is plus an authentication, what's called an authentication path. And this authentication path, it's meant to ensure binding. So it's meant to ensure that, in order for the prover to successfully provide a valid authentication path, like basically that prevents the prover from changing its mind when it learns what UI is. So this ensures binding. It ensures that once the prover sends the commitment, it can't change its mind about what vector lives inside the commitment. So it can't change U. Okay. So let me explain how Merkle trees work. So the commitment to U will just be one hash value, and I'll explain now how that hash value is determined. Okay. So let me just say U has length 4. 3204. Okay, so what the Merkle tree will do, again, I'm trying to make this quick, is it will just pair up elements of U and hash them. So that kind of reduces the length of the resulting vector from 4 down to 2, right? Because we took every pair of elements of U and we hashed them to get a single hash value. So now we only have n over 2 hash values. And then we pair up those hash values and we hash them. And in this example, that would reduce us down to just a single hash value. That is called the root of the Merkle tree, of the Merkle hash tree. And that root value, that hash, that is the commitment. So that is what like the prover sends as the commitment to you. It's just that one hash value. Okay. So now if the verifier says, hey, I want to know UI, says, tell me UI. Okay, so the prover will, if it's honest, will send 0. And then to prove that 0 is indeed, the third entry of the committed vector, it has to provide this authentication path. Okay, now what that authentication path is so you look at all of the nodes on the path from the root to this particular leaf. Okay, so these 3 nodes, and for each of them, you identify the sibling of that node. So these would be the 2 siblings. So this is the sibling of of this node, and this is the sibling of this node. And these hash values, these values are the authentication path. So the authentication path is basically just what I put in green, right? So the authentication path is literally these 3 green dots. So there's the claimed answer 0. There's the paired up entry of U, which is 4, and then there's this hash value. Let me call this Z1, and this hash value I don't know, Z2. Yeah, so 0, 4, and Z1. This would be the authentication path in this example. Okay, and what the verifier checks is that So in this example, V would check that Z2 is indeed the hash of 0 and 4, and it will check that the root is indeed the hash of Z1 and Z2. Okay, so basically what the verifier does is it goes up the root to leaf path, or the, I guess if you're going up the path, it's the leaf to root path. Okay, and it sort of infers via hashing, just by hashing the appropriate two nodes. It infers the value of that node in the leaf to root path, and then finally it checks that the inferred value of the root matches the commitment. Okay, and the key observation for binding or security is that the prover is not able to, or the committer is not able to open any entry of the committed vector to two different values unless it can find a collision in the hash function. Okay, so let me write that out. So suppose like a prover can produce two values, UI and let's say UI prime. They're not the same value. And authentication information for each. So authentication paths for each. So this would violate binding because this would say the prover is able to open entry I of U to two different values, UI and UI prime. Okay, and the claim is the two authentication paths, somewhere in them, must contain a hash collision. Right. So if we're using like SHA-256 as the hash function, we don't believe anyone can find a collision in that hash function with like a feasible amount of computational resources. So it's basically just an impossibility. The prover cannot break binding without violating the assumption that computationally bounded adversaries can't find a collision in the hash function. Okay. So in this situation, the two authentication paths must contain a hash collision. So that is two different, like inputs to H that hash to the same output. Okay, and what's happening is because they're valid authentication paths, so let me just do it in this little example that I drew. So here we have like the root. We had these values sort of Z1 and Z2, and then we had the entries of U, U1, U2, U3, U4. And let's say, let's say the prover was able to open U3, actually open this third entry to two different values. So the two authentication paths would be, like the first one would be root. It would have Z1, Z2, U3, and U4. And the second one would be root, and it would have Z1 prime, Z2 prime, U3 prime, and U4 prime. Okay, and it has to be the same root, for both. Okay, so what that means is that like the hash of Z1 and Z2, as well as the hash of Z1 prime and Z2 prime, they both have to equal the root. Okay, so if Z1 and Z2 is not the same as Z1 prime and Z2 prime, we found our collision. We're done. Right. If Z1 and Z2 are the same as Z1 prime and Z2 prime, we haven't found a collision yet. But we do know that U4 and U4 prime are not the same. It was U3 and U3 prime are not the same by assumption. So these are not equal. So we've really just pushed the presence of a collision like further down the authentication path, right? So if Z1 and Z2 are and Z1 prime and Z2 prime are the same, then we know that what is it? We know that H of U3 comma U4 equals Z2, and we know that H of U3 prime comma U4 prime equals Z2 prime. So if Z1 Z2 is the same as Z1 prime Z2 prime, now we have found our collision because we know that these U3 and U3 prime are not the same. So kind of either the collision like lives at the root, or it lives just below the root in this example. So in general, it's like you kind of walk from, because the roots in the two authentication paths are the same, but the leaves are not the same. there's got to be a collision somewhere along the path. So if it's not at the root, it's, somewhere below the root. If it's not one step below the root, it's somewhere below that. If it's not two steps below the root, it's somewhere below that. And at some point, you either found a collision or you get to the leaf. By assumption, the leaves are not the same. So at that point, you've definitely found your collision if you haven't already found one. Okay, so that's Merkle hashing. So hopefully I didn't go too fast or too slow, given that it was review for most people, probably. Does anyone want to ask a question about that? Cool. All right, so with that out of the way, I can pretty quickly sketch how these polynomial commitment schemes work. Now, again, it's very much a sketch. In fact, I'm not even going to tell you a complete polynomial commitment scheme. I'm going to tell you a straw man, which gives sort of like the very main idea of how these polynomial commitment schemes work. But there are some issues that prevent it from actually being a polynomial commitment scheme. And we'll have to defer explaining in detail how to address those issues for a few more weeks. Just note that the length of the authentication paths is logarithmic in the size of the committed vector. Okay, so yeah, these are one authentication path is pretty small. So think of that logarithm as maybe 20 or 30, or if it's a huge vector, it might be 40. And like 20, 30, 40 hash values, not that much data. That's fine. So where you get that snarks like polynomial commitment schemes like Fry turn into pretty big snark proofs, like hundreds of kilobytes in size, is because the proofs wind up consisting not just of one authentication path, but many authentication paths. And that's what really makes them big proofs. Okay, so yeah, here's the straw man. Okay, and this is like a natural approach to try to give a polynomial commitment scheme, but it's going to have two issues. One is a performance issue, the other is a security issue. So this is a straw man polynomial commitment. Okay, so what we do is we just have the prover, like in its own head, materialize the vector of all evaluations of the polynomial it wants to commit. All right, so let's call that polynomial P. Okay, and there are two example kinds of polynomials that come up in snark design. Typically, you're either dealing with P being univariate, claimed to have degree at most, let's say some bound D. Typically, D is something like the size of the circuit that the prover is claiming to have evaluated correctly on the witness. In the case of GKR-based snarks or Spartan, P will be, this polynomial P will be multilinear. And the number of variables will typically be order. It might be typically it actually, yeah, let's say order the logarithm of the size of the circuit that the prover is claiming to have correctly evaluated, roughly. Many variables. Okay. Either way, these would be pretty big polynomials. Like, if the degree is, the size of the circuit, then like the number of coefficients of the polynomial is like as big as the circuit. Circuit you should think of as being, it's big enough that we don't want the verifier to like evaluate the circuit on its own, gate by gate or something. So they're pretty big circuits. And similarly, a multilinear polynomial in this many variables, like the number of coefficients it might have is also like size of circuit. That's why the prover is committing to the polynomial instead of just explicitly sending it to the verifier. Okay. So now this vector of all evaluations of the polynomial, like it is a huge vector, and that's the performance issue here. So if you're dealing with a univariate polynomial, the number of evaluations this polynomial takes, the number of inputs to this evaluations is size of field. Like you can evaluate the polynomial at any field element. Okay, so think about working over a field of just, for example, a size about 2 to the 128 or 2 to the 256 or something. So it's just, it's literally infeasible for the prover to actually write down all of these evaluations. And the situation is even worse for the multilinear situation. So if the number of variables here is L, the number of evaluations in that case is field size to the L. Okay, so that's like, that's even worse. That'd be like 2 to the 256 times log circuit size or something, which might be like 20 or 30. I mean, that's, just totally nuts. So the prover can't actually write down this whole vector. Let's just ignore that for a second. If we ignore that, then what the prover is going to do is write down this whole vector of all evaluations. So like P of 0, P of 1. This is in the univariate case, P of 2, all the way up to P of size of field -1 if it's a prime order field, and just build a Merkle tree over this thing. And the commitment to P, we're going to think of as just being the Merkle commitment to this vector. Okay. So we took this huge vector and we committed to it with just a single hash value. Okay. Now when the verifier wants to know P of R, so that, the polynomial commitment scheme has to allow the prover, P needs to be able to reveal P of R as well as a proof that the revealed evaluation is consistent with the committed polynomial. Okay, and that seems simple because that's the whole point of Merkle trees, which is, it seems like we can just have the prover, so P of R is by design just the rth entry of the committed vector. So the prover can just reveal the rth entry of the committed vector and its authentication path. Okay, so that's great. That works. And in fact, from the verifier's perspective, even though the prover took a completely unreasonable amount of time to materialize this vector and commit to it, from the verifier's perspective, this would not be so bad, because even if this vector has size, say 2 to the 128, because that's how big the field is or something, an authentication path would consist of only like 128 hash values, which is not that many. I mean, that's kind of okay. So the problem, even from sort of the verifier's perspective, is not a performance issue. It's a security issue. And that is this approach, this scheme I just described, which is literally just like Merkle hash like the evaluation vector of the polynomial. There is no guarantee that the committed polynomial satisfies the claimed degree bound. Right. So when the prover sends like the Merkle root, it's binding itself to some vector, but there's just literally no guarantee that about the contents of that vector. In particular, the vector might actually be all evaluations of a very high degree polynomial, not a low degree polynomial. So there's no guarantee that the committed polynomial has degree at most d. So has degree less than like kind of the maximal possible degree of any polynomial, which would just be, if you only care about its input-output behavior anyway, which would be field size -1 or something. Okay, so there are, so something like Fry has to address both issues. So we have a prover time issue here, okay, and we have like a low degreeness issue, that the above straw man doesn't actually ensure that the prover is bound to a low degree polynomial, or just binds it to, some function, some polynomial, which could have arbitrarily high degree. Okay, so let me just briefly sketch how both of these things are addressed. So the prover time issue in something like Fry, the prover will only Merkle commit, not to every single evaluation of the polynomial to be committed, but only a relatively small set of evaluations. So only to evaluations of P over a small subset of the field. So in Fry, and I'm focusing on that because it's the most popular one today in this category, that subset is typically like all nth roots of unity in the field. And if you don't know what that means, don't worry about it. We'll talk about it in a few weeks when we get to Fry, where n is some constant factor bigger than the degree. So like 4 times the degree or 16 times the degree or something. And so that's how you solve the prover time issue, is it does not have to actually like write down and then Merkle hash every evaluation of the polynomial. It only writes down like 4 times degree or 16 times degree many evaluations of them. This does create complications, and they're actually quite subtle and probably underappreciated. If the verifier like wants to evaluate P of R, during like like after the commitment descent, for an R in the field outside of this small set. So that's not say the nth root. That's not an nth root of unity. So there are ways to deal with those complications, and that's all I'll say about that right now. Okay. Then regarding this low degreeness issue, okay, so the conceptually simplest way to address this issue is to just tell you that there's something you should just treat it as like some magical mathematical result called a low degree test. Okay, this says that it is what I'm about to say is an oversimplification, and I'll explain the reality in a moment. So the oversimplification is the following. This will let you, so a verifier can sort of check whether a polynomial P is low degree by inspecting it at only a few points. Okay, so the idea is, like the prover is like committed to this giant vector. The verifier, until it starts looking at entries of the vector, it has no idea if this vector is actually like all evaluations of a degree D polynomial. And what a low degree test lets the verifier do is sort of inspect only a few entries of that committed vector and get a pretty good sense if the polynomial is actually low degree or not. And I'm not going to tell you how so it's choosing these points to inspect in like a very special structured way. And the details are not important for today. Now this is a lie. Like, unfortunately, if you only inspect a few evaluations of a function of a polynomial, it's impossible to tell if it's truly low degree or not, because the prover could, for example, take a degree D polynomial and modify its evaluation at just a single input. And now it might actually, its degree might go from D all the way up to, something as big as can be. So just by changing one evaluation of a low degree thing, you can make it very high degree. Okay, and if the verifier is only inspecting a handful of evaluations of the polynomial, there's like almost no way it's going to detect some kind of very small change to a low degree thing. It'd have to get very lucky to kind of happen to inspect the one evaluation that was changed or something. So it can't actually check whether the polynomial is low degree. It can only check whether it is close to low degree. And what that means is it can basically get the guarantee that, like, if the prover passes the low degree test with non-negligible probability, then there exists some degree D polynomial, degree D polynomial, say P prime. P prime might not exactly equal P, but P prime and P will be guaranteed to agree for like a large fraction of inputs X. Right. So basically, if the prover kind of, committed to something that is not roughly of the form like take a low degree thing and modify its evaluations on a relatively small fraction of inputs, the low degree test will detect that the prover committed to something that's, nothing like low degree. So, and what something like Fry is, as well as really everything else in this category, Laharo, breakdown, etc., they're kind of like interactive variants of low degree tests. So they're a way for the verifier to kind kind of gain a lot of confidence that the Merkle committed vector is close to low degree. But because they leverage interaction, meaning, you know, the prover, the verifier will send like a random challenge to the prover who has to reply before receiving potentially another random challenge and replying again and so forth. So they're leveraging interaction at a very high level to kind of reduce the number of points that need to be inspected, sort of. So the reason to use interaction here is to sort of improve the costs of known low degree tests. Okay, so low degree tests like are actually what you want. There's an old, now it's fairly old literature on like low degree tests for PCPs, something called probabilistically checkable proofs, and those do not leverage interaction at all, and they're not really practical. So if you want literally like a probabilistically checkable proof, there's no the model itself does not allow interaction. And so while asymptotically speaking, there are these low degree tests where the verifier only inspects a few points. A few, concretely speaking, is actually not a few. So by leveraging interaction, things like Fry and Laharo sort of reduce the concrete cost of these low degree tests, both for the prover and the verifier. And roughly speaking, they lower the number of points that the verifier has to inspect, thereby limiting the number of Merkle authentication paths that the prover has to provide that must ultimately wind up in the SNARK proof, right? Because every time the verifier wants to inspect an evaluation of the committed vector, the prover has to provide an authentication path to sort of justify that the provided element of the vector is honestly provided. So we'll talk in more detail in a while, maybe 4, 5, 6 weeks or something, in detail about exactly how we avoid having the prover commit to all evaluations of the polynomial and instead have it commit to only like a constant factor more than the degree many evaluations, and explain details of how the low degree tests work, especially because they're interactive. Okay, so hopefully this was not too fast and enough information that in the coming weeks, when I say, well, now you apply a polynomial commitment scheme, you have some idea of how that polynomial commitment scheme might work, so it doesn't feel quite so magical to you as if I hadn't gone through this sketch today. Okay, so that's everything I had to say. Please ask questions if you have any. Again, I hope it wasn't too fast or too slow. And if you don't have questions, thanks as always for your full 90, I don't even know how long we've been here, 2 hours, for your full 2 hours. And yeah, next week we'll see Spartan, which I think is a lot of fun. So I look forward to that.
Thank you very much.
Yeah, thank you.
Oh, thank you.
Yep. Have a good weekend.
Thank you.
Thank you.
Can you elaborate on the why Fry why air each transition function is the same? Like,
Why each what function is with air?
Transition constraints or
so you for
like last week.
like when you turn like a virtual machine or CPU abstraction into a circuit, why it's like the virtual machine abstraction is why it's I'm saying it's applying the same simple transition function over and over and over again.
Yes, because each instruction is different, right?
Yeah, but the idea is well, there's sort of there's a more and a less technical caveat. Okay, so the less technical one is that the number of instructions in your instruction set is regarded as constant. So in practice, it might be it might be like 100. So like RISC-V is somewhere, depending on what instructions you can, I think it's somewhere between 60 and 120. The EVM, I think, is I don't know, like I don't know exactly, 140 or something. Cairo is like a very simple instruction set, and it's much less. Might have as little as like, I don't know, under 10 instructions or something. So yeah, like 140 is like maybe, shouldn't be regarded as constant, but like theoretically it is. So the point is, no matter how long you run the program for, the number of possible instructions in this instruction set is fixed. So that's why it's constant. It's like that. It's independent of the runtime of the program. Okay. So once you consider this constant, I think maybe your question, the answer sort of maybe becomes clear, because like even if you at that point, like a circuit, sub-circuit or something that directly implements every possible instruction is itself sort of constant size. And when I say constant size here, it depends really how many registers there are, and like, are you counting what's your primitive data type, does it fit in one field element or whatever. But let's sort of hand wave over those issues and just say, like, if there are constantly many instructions and each instruction sort of takes, is thought of as a primitive operation or something, so it can kind of execute in just like one time step, then a sub-circuit that directly implements every possible instruction is of constant size. Okay. And then so running like a program for this that for like a billion steps, all it does is a billion times it will do the following. Run a program for a billion steps means 1 billion times do sort like read like the program counter, or basically what I really mean is like figure out what instruction to execute at this step, which of the 140 instructions to execute at this step, and then execute that instruction. Okay, and that's it. So this is what the computer program does. If you run the program for 1 trillion steps, it just does this 1 trillion times. And so that's what I mean. And then this thing, this whole thing is just a constant size. There's a circuit that implements this constant size. Right, like half of it, like I covered execute that instruction up here. So this second bullet point, execute that instruction, that's what I said up here. And then this logic to just like figure out what instruction to execute at this step, that just sort of amounts to like reading like a program counter or something. Like the program itself is just storing in one register or something, like the which instruction should be the next one to be executed. So like that's sort of trivially like just like one read operation or something. So yeah, was this clear enough an explanation? I know it's pretty hand wavy, but did that give the main idea?
Yes, but like, so it's only constraining, so read the program counter and figuring out what's the next instruction, but wouldn't the prover cheat by like choosing a different instruction? Like,
Yeah.
why the prover can't do that?
Oh yeah, it's because the logic to like update the program counter at each step and basically indicate like what is the next instruction to be executed is like part of the previous instruction. When the prover goes like at time step I to execute that instruction, like part of what that means is like that instruction contains logic to tell the program what instruction should be executed at the next step. So as the prover proves at each step that it executed each instruction correctly, that sort of implies that reading the program counter, in the following step will reveal the appropriate instruction to execute next. So in a word, it's like when the program goes to read the program counter. Okay, this program counter is not like an untrusted advice input. Okay, that program counter was set by the program in the previous step. Did that make sense? The prover does not have free reign to just like change what instruction gets executed at each step. The program itself determines what instruction gets executed at each step.
Yes, kind of makes sense. Is there a like paper on this?
I have not really seen great discussion of this, and I'm a little worried about people do seem to find this confusing. And I'm about to put out a paper on like new front end techniques, especially in the context of exactly what we're discussing. So like relatively simple virtual machine abstractions. And so these questions you're asking, I've like frequently encountered them as I've tried to discuss these topics with people. And I have not found like a great reading material or like ways to explain this that don't cause people to ask exactly the questions you're asking. I will say exactly the sort of thing we're describing is like kind of the prevailing paradigm for a lot of the prominent projects now. So Cairo, Risk Zero, they are precisely doing this, and like to a large extent the EVM projects too. They're using these virtual machine abstractions, and so this is what it means to use a virtual machine abstraction: is the prover's claiming to have run like the virtual machine for some number of steps, on some witness or whatever, some committed input or something. So they're all doing what I'm trying to describe to you. So you could try looking at like the Cairo, the Cairo ePrint, the Cairo documentation on ePrint. You could try looking at that. You could try looking at, I guess, what some of the EVM projects have written, but I don't think that those are very readable or detailed. Risk 5 recently put out like a white paper. I didn't look at it carefully. I doubt that it, discusses this in great detail. So I don't know, if you need something to read, maybe look at the Cairo documentation on ePrint. But I don't have like here is a great exposition that clarifies all these issues, and like to point you to for sure. Does that make sense?
Yes, thank you. Cause when I want to like understand error, it's all like couple of blog posts, and yeah, and they just it's not super clear, I guess.
Yeah,
So
yeah, yeah. I don't know exactly what to tell you. I mean, I think people generally like the blog posts, and so like both the Risk Zero project and Starkware have put out a lot of those blog posts and and some videos and stuff, and I think people do like them. But I think probably the focus there, I haven't looked at them carefully myself, is on like the back end machinery, as opposed to your questions are kind of about the front end machinery. Like, how do you kind of write a circuit that captures the virtual machine's execution, and how do you think about that circuit? And so again, if you're not happy with the blog posts, I think check out the Cairo documentation, and I think I will be writing blog posts shortly as I try to describe this new work that I have coming out soon, which is going to try to grapple with this stuff too. But I don't know that it's going to really do that much better than what we just discussed verbally here today. Yeah, but anyway, I'll certainly point you to those posts when they're available, if I think it would be helpful in answering these questions.
yes, thank you. Maybe I should also read the code and stuff.
Maybe, yeah. I will say this. One of this paper I'm putting out, which is sort of like a new front end for some of these virtual machine abstractions. That paper might be the thing to look at when it's done being written. Unfortunately, it's not fully written yet. But that might make a bunch of this stuff more concrete, potentially.
Yeah.
If we write it well, which will be hard. Yeah.
Yeah. Thank you.
Yeah. Thank you for the question.
Yeah.
Anyone else have questions? Cool. Okay, let's call it a week. Thanks again for all your time, staying even beyond the 2 hours. And I will see you next week, and we'll talk about Spartan. Have a great one. Talk to you soon.
Yeah, thank you. Bye.
Bye.